Uh, Hello, hi everybody. I'm going to talk about low temperature combustion and a work that we have done in the Universidad de La Mancha University using alternative fuels. This work is done together with Professor Hernandez and Rosario Ballesteros. So first thing we're going to see is what low temperature combustion is. Low temperature combustion is a family of combustion modes for compression ignition engines which try to simultaneously reduce particle matter and NOx, which is a really difficult thing, and especially when we try to keep the same efficiency of the engine. And the bad thing we usually have with this kind of combustion mode is that we increase total hydrocarbons and CO. So we can achieve that kind of combustion either with early or with late injection, start of injection of the fuel inside the chamber. And we also need to use high EGR rates. So what we try to do is, since this is a conventional diesel fuel, this is the way that takes the fuel inside the chamber in a conventional combustion process. Then in that process, it crosses the regions where particulate matter and NOx are formed. And we are trying to avoid that by using linear mixtures and lower temperature. So this is a typical process. This graph comes from a really good paper from OCULOS et al. That tries to explain a phenomenological model. And we have to take a look at the green line and the blue line. As we can see, heat release, the green line is heat release rate, and as we can see, heat release rate begins after injection ends. So that's a highly premixed process. And then we also can see that we have three stages. A first, that we call first stage, which is a consequence of low temperature reactions of the fuel. Then the main stage, which is the largest heat release, and then finally the residual heat, which is released in a mixed control process. So our purposes in this work was to achieve this kind of combustion in our facilities and to do that with different alternative fuels. And we will take a look to both our facilities. This is our facilities, which is equipped with a single cylinder engine. It's a 2-liter single cylinder engine, which is correspondent to a heavy duty engine. And we also have a independent controlled common rail system. These are the conditions that we have tried, and as you can see, we have kept constant engine torque, speed, intake pressure, intake temperature, pressure of the rail, and EGR rate, which as you can see is really high. And we have moved the start of injection from 12 degrees before top dead center to 4 degrees after top dead center. So this is a scheme of our facilities. Let me highlight just a couple of things. We can control EGR. We have kept it constant in this experiment, but we have the chance to change it in future work. And these two things are the equipment that provide us the results that I'm going to show. First of all, the emission results, and second of all, the pressure shape from the cylinder allows us to calculate the heat release rate through a diagnostic model. These are the tests that we have tried. We have a conventional diesel, a mixture of diesel and ethanol, and 10% in volume, and a GTL, which is a fuel that comes from a Fischer-Tropsch process. It's a mixture of alkanes. And there are a lot of properties. I'm going to highlight two. Low heating value, and we have diesel, which is in the middle of e-diesel and biodiesel, being e-diesel the one that has lowest energy content, and GTL the one that has highest. And set and damper, that happens more or less the same. E-diesel is the one that has less tendency to auto-ignite, while GTL has a really high tendency to auto-ignite. So the first thing that we have detected while doing our experiments is with diesel and d-diesel, results from 4 degrees after top dead center was not really repetitive. So we have, these are as an example, I'm showing these are 20 consecutive cycles taken in the same experiment. As you can see, the cycle-to-cycle variability deteriorates very much while delaying the start of ignition. That's why we cannot use the diesel and DDC results. The only fuel that has allowed us to work in such delayed start of ignition angles was GTL. So the first thing that we are going to do in the next slide is try to analyze if we are really achieving LTC combustion or not, which was the first purpose of this work. So these are in these next slides, we'll see heat release rates from diesel, e-diesel, and GTL, and in this point you will be able to see the start of ignition angle. So this is the more advanced ignition angle, as you can see, especially for diesel, and GTL is pretty conventional diesel combustion. Pretty much the same at 4 degrees before top dead center. And we also can see that both in this case and the previous one, that this is the start of injection, and this is the start of combustion. The ignition delay, which is the difference between the two of them, is much lower for GTL than for diesel or e-diesel, which was expected since the Zetan number is much higher. So we have the same 4 degrees before top dead center. At top dead center, the e-diesel heat release shape begins to change. We have something that we are not sure, but maybe a consequence of low temperature heat release, and that shows clearer at 2 degrees after top dead center. In GTL we have conventional combustion as the other cases, but in diesel and e-diesel we have a pretty clear that, I'm not sure if you remember, but the shape is really similar to the first slide where we were explaining how the LTC combustion should be. And we have a first stage heat release, a second stage heat release, or main heat release, and finally a mixed control process. So the first objective is accomplished. It seems that we are able to achieve this kind of combustion. Then we're going to take a look at the results that we have obtained with performance. As we can see, especially in this figure, because this is specific fuel consumption, and this is going to change because the energy contents of the three fuels is different, but if with the efficiency, the energy content does have not influence, and we see that the fuel efficiency decreases when delaying start of ignition, which is expectable since we are not centering, we are delaying the combustion process from a center one. So we are deteriorating the efficiency. When taking a look at carbon monoxide, at total hydrocarbons, we see a really, really sharp increase after top dead center. What was expectable is really common with LTC processes. And what we did not expect it was these results. We expected these ones, which are good. We are decreasing NOx and in a really large rate. We are using both high EGR and really delayed start of ignition, so we were expecting really low levels of NOx, but we were expecting a change in these values. We were expecting that particulate matter will decrease after top dead center, and we have not obtained that. So, and these results are consistent with SMPS results, except in this case, the other ones are really, really consistent. So we are confident in the previous results, and we have to find out. We think that we know the causes. We think that globally we are working on really rich mixtures, so we are not avoiding the region where particulate matter is formed anyway. So we have to try to do some more experiments to avoid that. And we also see from these results that what we obtain is from 12 degrees before top dead center to top dead center, more or less, we are increasing both size and the number of particles. And from top dead center, we are increasing, especially we are increasing the number of particles from the same size range. So as the main conclusions that we have been able to achieve LTC in 2 of the 3 fuels. It has not been possible with GTL. We are achieving conventional combustion in all the cases, even for really, really delayed start of ignition. And this delay of start of ignition causes deteriorating efficiency, higher total hydrocarbons and CO, and particulate matter, which we are expecting in the next experiments we will be able to decrease that. And we have really, really low levels of NOx, which is good. The next experiment, the future work, what we want to do is to increase the intake pressure, and that way we will move from so rich mixture to linear mixtures, and we may be able to avoid the region where particulate matter is produced. We also want to try with a biofuel from fatty acid transesterifications and do some kinetic modeling, trying to figure out what's happening there. So, thank you very much. If you have any question.
Thank you very much.